Inverse relations. An inverse relation is a set of ordered pairs that is the result of swapping inputs and outputs in a relation. Here are two examples. In example A, we have 0 mapping to 2, 1 mapping to 5, 2 mapping to 8, and 3 mapping to 11. S inverse, in this example, begins at 2 and maps to 0, then begins at 5 and maps to 1. Begins at 8 and maps to 2, and begins at 11 and maps to 3. In example B, we have this relation T. In the original relation T, -1 maps to 2, 0 maps to 0, 1 maps to 2, and 2 maps to 4. In T inverse, the original outputs become our inputs. So we have 0, and it's mapping to 0. 2 is mapping to -1 and +1, and 4 maps to 2. Let's take a closer look at both of these examples one by one, starting with example A. So here are properties of inverses that deserve our attention. We have that 0, 2 is contained in our initial set S, and that implies that the point 2, 0 is contained in the set S inverse. And that is definitely true. 0, 2 is in S, 2, 0 is in S inverse. The domain of S is now the range of S inverse, which is 0, 1, 2, and 3. The domain of S inverse is equal to the range in relation S, which has values of 2, 5, 8, and 11. In this example, both S and its inverse are functions, because for each input there is one output, and for each output there is only one input assigned to it. So we're going 1 to 1 in S, and we're also going from 1 to 1 in S inverse. Now let's look more closely at example B. We had our relation T mapping from -1 to 2, 0, 0, 1 to 2, and 2 to 4. And T inverse maps from 0 to 0, from 2 to -1 and +1, and then it maps from 4 to 2. Are these statements true or false? -1, 2 in T implies that 2, -1 is contained in T inverse. That is a true statement. And we basically mapped each one, -1 to 2, that's there, and then 2 to -1 is also present in T inverse. Now let's look at the second one. The domain of T, this oval, is equal to the range of T inverse over here. Well, that is also true. Let's look at the next one. The domain of T inverse, okay, that's this set of values, is equal to the range of T, this set of values. And indeed, those are equivalent, so this is also true. True or false? Relation T is a function. For every single input, you have exactly one output. That is also true. Now let's look at T inverse. T inverse is a function. This one is going to be false, and the reason that it is false is because 2 maps to both -1 and +1, making it not a function. And here are the solutions to this example, and they do match the solutions that we found. The first 4 were true, and the last one was false. Here's a summary of the inverse relations that we have looked at. The properties of a relation S and its inverse relation match these 3 conditions. If the point A, B is contained in relation S, then the point B, A is contained in S inverse. The domain of relation S is equal to the range of relation S inverse. And the domain of S inverse is equal to the range of S. If a relation is a function, its inverse relation may or may not be a function. In example A, the relation and its inverse were both functions, when we had exactly one output for every single input. In example B, the relation was a function, but its inverse relation was not a function, because the original relation had two x values that gave us the same y value, so therefore its inverse became not a function because you had two x values going to two different y values. Remember that if the point A, B is contained in the relation S, then the point B, A will be contained in or a part of the relation S inverse. This means that if the graph of a relation includes the point A, B, then the graph of its inverse includes the point B, A. So we're going to first complete this table. We have that one point has coordinates -4, 1, and it's shown in red. We're going to write down the coordinates of its inverse, and the coordinates of its inverse are literally found by switching the x and y coordinates around. So it will be 1, -4. This blue point is at -2, -3. Its inverse will be -3, -2. The green point is at 1, 3. So its inverse will be at 3, 1. The orange point is at 2, 5. So its inverse will be at 5, 2. And our purple point is at 3, -1. So its inverse will be at -1, 3. And here are the coordinates for the points on S inverse, and they do match the points that we had found. Now that we have found the points contained in S inverse, let's carefully sketch the graph of S inverse in the same coordinate plane that shows the points contained in set S. Let's begin with our red point, 4, 1. Its inverse we found was 1, -4. So 1, -4 is down here. So we're going to put a red X there. Okay, now we have -2, 3, -3. Its inverse is -3, -2. So let's put a blue X there. Now we have the point 1, 3. Its inverse was 3, 1. So 3, 1. We'll put an X here in green. And now we have 2, 5 in orange. So its inverse will be 5, 2. Right here. Now we have our point 3, -1. Its inverse was, or is, -1, 3. So if I go to -1 up 3, that's going to be where our inverse for the last point is found. Now let's examine the relationship between each of these original points and their inverse. Notice I'm traveling from the original point to its inverse on this diagonal line, and it's always shown on this diagonal line as the path from one to the other. That's not happening by accident. We are actually reflecting our original point about the line y equals x to find its inverse point. So let's actually draw that line of reflection in our coordinate plane. And now you can see that this is 1 1/2. Here's the half and here's the other one. 1 and 1, diagonal. We're going 1, 2, and we're going another 1, 2. 1, 2 1/2. Here's the half and 1, 2. We only want a half and a half diagonally to get over the line y equals x from the original point to its inverse point. In the coordinate plane below, the graph of S, which are all points, look like little dots, and S inverse, which are x's, are all shown. Each pair of companion points, A, B, and B, A, are positioned across the diagonal y equals x and are equidistant from the diagonal as we've shown when we originally graphed S inverse. This symmetry with the diagonal is a property of a relation and its inverse relation. They will always be equidistant from the diagonal line y equals x. In summary, the graphical properties of a relation S and its inverse relation are given below. The first one is that if a comma b is contained in S, then the point b comma a is contained in S inverse. You switch your x and y coordinates around. The line segment joining AB and BA is perpendicular to the line y equals x. And the intersection of the line segment joining AB and BA and the diagonal y equals x bisects the line segment. This means that they are equidistant from the line of reflection y equals x. So this distance from AB to the line y equals x and the distance from the line y equals x to BA are congruent to one another. Here's a proof explaining the properties of a relation and its inverse relation. Primarily, the second and third bullet points are being proven here. So the slope of the line joining AB and BA, it would be B minus A over A minus B. Now, how does that fully equal -1? Some of you may be asking. So let's rewrite B minus A over A minus B in the same form. We'll keep it as B minus A, so I'm going to leave the numerator alone. But if I reorganize these, I would have -b plus A, and then I can factor out a -1 in the denominator from both terms. So I would have B minus A in the numerator, and then in the denominator I would factor out that -1. The -b becomes now positive, and the positive A now becomes negative. And then the B minus A factors cancel one another out, so you are left with 1 divided by -1, which is equal to -1. The slope of the line y equals x is +1, and the product of their slopes, y equals x, and this slope is 1 times -1, which is -1. Some of you may also remember that perpendicular lines have opposite reciprocal slopes. Well, the slope of y equals x is 1, which is 1 over 1. So this is slope of y equals x. And then the slope connecting AB to BA is equal to -1 over 1. So if I flip 1 over 1 over and change the sign, it becomes -1 over 1. Again, making them perpendicular. And then to prove the midpoint, we can use the midpoint theorem. The midpoint theorem is add up the two x coordinates, divide by 2, so that's a plus b over 2. And here you would have b plus a over 2, which you could also rewrite as a plus b over 2, which lies on the line y equals x, as was demonstrated.